Good morning, everyone. So we are continuing with our study on optical isomerism. So in the previous class, we tried to learn how to draw a three-dimensional molecule on a two-dimensional plane using two different formulas. That was perspective formula, and another formula that we used was the Fisher projection formula. Now let us go further into the chemistry aspect of the optical isomerism. We studied that optical isomerism is actually a phenomenon in which it exhibits an effect on the plane polarized light. And we found that stereoisomers which are able to show optical isomerism are the ones that have this property of chirality. Only those molecules which are able to show chirality would be having this phenomena called optical isomerism. And we learned in the last class that for a molecule to exhibit chirality, it should have a three-dimensional spread over the space. Okay, so that is the fact. Those were the things that we studied, and we found that most of the saturated molecules come under this category of 3D spread. So that is why we focus our attention on sp3 hybridized carbon atom, and we looked into these molecules, which we are going to again see. So now we have looked into this chirality using various objects like screws, chair, hands. Okay. Now we are going to see the same property in molecules. Okay, and see whether certain molecules are able to show chirality or not. Let's look at the first example, that is dichloromethane. We are not looking into the example of methane because it's a perfectly symmetrical molecule, so obviously it won't have a non-superimposable mirror. So let's look at this example of DCM, that is dichloromethane. So this is one of the perspective formula that I have written down here, and this is the corresponding mirror image. I hope you can easily make out this particular image that I have drawn here. Now we have to check whether this image is superimposable or non-superimposable on this original structure. So what we have to do for that, we have to somehow make this particular image orient in such a way that it should come equivalent to this or non-equivalent to this. For that to happen, it can be easily visualized that we can along this CH bond, taking CH bond as the axis, if we rotate this molecule by an angle of 180 degree, what will happen? This H will come exactly like this particular molecule. So when we rotate this molecule by an angle of 180 degree along the CH bond, when we rotate this molecule by an angle of 180 degree, what happens? You get a structure something like this. I hope this is pretty simple, because when you turn it, this molecule would be turned in H here, and then you have again the solid and the dashed with, and since both are chlorine, wherever you put, there's no difference. So what do you find here? This particular structure is perfectly equivalent to the original structure. So that means these are superimposable. So that means these are not chiral. They don't exhibit the property of chirality. Well, let's look at the other example, which is your bromochloromethane. So this is the original perspective formula that I have written down, and this is the corresponding mirror image. Okay, this you can easily visualize that this structure is the mirror image of this original structure. Now we have to check whether these two are chiral or not. For checking that, what you have to do, you have to turn along this CH bond, because you should bring this bond exactly like this. Only then you can compare these two structures. So you have to rotate or do something so that it could be made similar to that, so that we can do a comparison. So for that, what you have to do initially, you have to rotate across this along this CH bond. You have to rotate by an angle of 180 degrees. Okay, so along CH bond, when you rotate by an angle of 180 degree, what happens is H will come on this side. This is pretty similar to the original structure, and obviously you have the dash bond and the wedge bond you have drawn. So when you rotate it by an angle of 180 degree, what will happen? The back side Cl will come on the front side, and the front side Br will go on the back side. So when you rotate this molecule by an angle of 180 degree, what happens? Br will go to the back side, and Cl is going to come on the front side. So when that happens, you see that these two molecules are not equal. These two molecules doesn't look equal because here Br on the front and here Br on the side. Like if we do another operation along this axis, suppose axis A, okay, along axis A, if you rotate it by an angle of 180 degree. Now, along the axis A means, which is the axis? If suppose HCH, this is the bond angle, then you bisect an axis so that it passes through the middle of this HCH angle and this CL CBR angle. So it passes through the middle of it, and you do a rotation of clockwise or anti-clockwise, whichever you want to do. When you rotate by 180 degree, what happens? These two will flip. These two will flip. And this two will also flip. So what happens? Br will come to the front and Cl will go to the back. So now what do you see? These two molecules are perfectly same. That means the mirror image and the original structure, they are the same molecule. So that means these doesn't exhibit the property of chirality. So these two molecules will never show optical isomerism, because to show optical isomerism, the molecule should be chiral. So since they are not exhibiting the property of chirality, these two examples will never come and fall under the category of optical isomerism. Now let's look at the third example, which is bromochlorofluoromethane. Bromochlorofluoromethane. So I've drawn one particular perspective formula here. So here the difference is all the atoms that are attached now to the central carbon atom is completely different. So this is the corresponding mirror image. So if I want to compare these two structures, I have to bring this mirror image in such a fashion that I can compare them both. For that, like I did, it can be easily compared if I rotate along the CH bond by an angle of 180 degree. So if I rotate along the CH bond by an angle of 180 degree, what will happen? F will come on this side. This now looks similar, but what happens? The Cl has come on the front and Br on the opposite side. But so this is not comparable. So like we did here, we can do one more 180 degree, but what will happen? Then if you do that, this thing will completely change. Because if you rotate it by 180 degree along this particular A axis, what will happen? F will come on top and H will come below. Though your Br would come on front and Cl will come on the back side. But what do you see? These two are not equal. These two are not equal. So here we see an example where the mirror image is not superimposable on its original structure. So these molecules will exhibit the property of what you say chirality. These the properties molecules in which all the four atoms, that is atoms or groups attached to the carbon, is different. They will exhibit the property of chirality, and in molecules we say they exhibit the phenomena of enantiomerism. Enantiomerism. Now, what do you mean by enantiomerism? Enantiomerism is a phenomenon in which the molecule or the stereoisomer is able to exhibit the property of chirality. I'll tell once again. Enantiomerism is a phenomenon in which stereoisomers are able to show the property of chirality. Okay, so whenever a molecule or a stereoisomers is exhibiting the property of chirality, we say that they exhibit the property of enantiomerism. And those stereoisomers which are able to show this phenomena of enantiomerism, they are called as enantiomers. They are called as enantiomers. Those molecules which are able to show the phenomenon of enantiomerism are called as enantiomers. Now I will come across another term. Now, whenever this carbon atom, I told you, whenever it is attached to 4 different groupings or atoms, they will exhibit the property of phenomena of enantiomerism. So, whenever a molecule contains a carbon which is attached to 4 different groupings, this particular center, because of which they are showing the property of chirality, is called as chiral center. They are termed as chiral center, this center, or they are also called as stereo center. They are also called as asymmetric center. Okay, so these are centers. If a carbon center is attached to 4 different groupings, these are the terms that we use for it. They are termed as chiral center, stereo center, and asymmetric center. So whenever you are talking about carbon atom, you will use this term of asymmetric center. Generally, when you talk about any center because of which there is stereoisomerism being coming into the picture, those we use this general term called stereo center. But in general, when we are not specific, we can talk about chiral center also. This is particularly used only when we are talking about a carbon atom which is attached to 4 different groupings. So they would be called as the asymmetric center, and these are called the asymmetric carbon atoms also. Okay, so these are the terminologies that we have learned in today's class. I would like you to just re-listen to what I have told about these particular terms, and please go through it, memorize it, not memorize it. I would never say that you memorize it, just understand it, what I have said it, so that once you know that picture, you can define yourself all these particular terms. So we will be discussing more in detail about all these terms in the classes. So till then, have a nice day. Thank you very much.